Scientists have been giving lectures in this theatre for nearly 200 years. But 80 years ago, almost to the day, something special happened.
Lecture 1, The World of Captain Gulliver.
The BBC transmitted a Christmas lecture using a brand new technology, television.
Thank you.
Science TV was born. So to celebrate, we're recreating famous demonstrations and inviting Christmas lecturers past to the stage to help out. The subject of these lectures goes back to their founder, Michael Faraday. It governs everything we do, from the nuclear furnace in the sun to the daily school run. It makes the whole universe tick, and getting enough of it is one of the biggest challenges facing the whole human race. That subject is energy. Welcome to the 2016 80th Anniversary Christmas Lectures. This lecture theatre consumes a huge amount of energy. We've got the lights, we've got the cameras, and we've got some air conditioning too. They're all energy guzzlers. We can see on our giant meter here. So this is no ordinary energy meter. We want to show you units of energy in a slightly different way. We're using AA batteries. So how much do we need for this lecture theatre? So running these lecture theatres requires 21,567 AA batteries. When I pull this lever here, all of that will be turned off. So tonight's challenge is, can we generate enough energy to power this lecture theatre? So along the way, I want to show you the amazing thing called energy. So let's do a countdown. 3, 2, 1. So this small candle is a good place to start. One of the greatest scientists, Michael Faraday, worked here at the Royal Institution. He gave Christmas lectures on the chemistry of candles in this theatre around 150 years ago. And this is one of his favourite demonstrations, which I'm going to try and repeat. It's basically, can I relight that candle when I put it out without touching the wick? It's a bit tricky, but I'll try. Okay, so let's see. Okay, you might have missed that. That was very quick. But fortunately, we have that in slow motion. So let's see that in slow motion. So you can see the vapour there. That's the vapour. And it's going to relight. And look at that. It's going to relight the flame. So what's happening there? Well, when you think of a candle, you think that actually it's the wick that's burning. But that's not quite right. What's happening is that the wax vapour comes up off the candle, and that is the chemical store. And if you time it right, you can actually relight the candle without touching the wick, as you saw in that slow motion. So it looks as if the wick is burning, but it's not, it's the wax. And the wax, as I said, is a great energy store. And this tells us a very important thing, a principle about energy. Energy can never be created nor destroyed. It only converts from one form to another. In this case, the candle is converting the chemical energy in the wax to light and heat. There's another important principle. When energy is converted, we can actually use it to do work. And a simple example is, again, using this candle and a fan. Okay, so if you see that, you can see it's turning. So what's happening here is that the heat from the candle is rotating this fan. In fact, one definition of energy is the ability to do work. So let's get back to our energy meter. How does the candle score? So remember, to power our lecture theatre, we need to get up here. So what does our candle give us? So, okay, so we're going to see it's going to drop down, drop down. Okay, 31 AA batteries. Actually, it's more than I expected. We can see it's not going to be enough to power this lecture theatre. So we can scale up a candle to make it more powerful. Okay, so what we're coming on now is a very special candle. It's made of something called gun cotton, which you can't get in the shops. Okay, we're going to see if it's different from the earlier candle. Let's see how it does. Right, fortunately, I'm sure you all saw that. What I'd love to see is in slow motion. Okay, so we've got it in slow motion. So let's have a look over here. So you can see there's the candle there. There's my long wick. And there you go. So you might think that this candle had a lot more energy than that small candle over there. Actually, the difference isn't that much. And the reason is, the main difference is to do with power. Scientists are very careful about these two words. They want to distinguish the word power and energy. While both candles have about the same amount of energy, the gun cotton candle, the one I just burnt, releases that energy all at once. It's a lot more powerful. So power is simply how fast energy is transferred. So I've already shown you that a candle stores chemical energy and it turns it into light and heat. But energy comes in loads of other different and amazing forms. And to help me explain this, it's a great pleasure to introduce a former Christmas lecturer, Professor Richard Dawkins. Hi there, Richard. Good to see you. Richard, it's a great pleasure, and I'm glad you could join us for this 80th anniversary lecture. You did an experiment that I really enjoyed watching about 25 years ago, back in 1991. And we've got a clip here.
I'm going to stand here, and I'm going to release it. And it's going to go over there, and it's going to come roaring back towards me, and all my instincts are going to tell me to run for it.
The whole principle is you can't gain energy, so it should swing back roughly to its original position. It can't go any further. But what do you remember about that experiment, and why did you want to do it?
Well, I think you're interested in conservation of energy. I was interested in showing my faith in science itself. As it were, putting, if not my life on the line, my head on the line.
So we're going to try and recreate it, but I have a confession, Richard. We have made a bit of a difference to the cannonball. We've added spikes. So we put a bit of a target here, and we're going to make sure it allows you to actually position your head perfectly. Right, so we're going to have a bit of a drum roll this time.
said last time was that I felt the wind a bit, and I did again this time. But I was told by Robert May, a very distinguished Australian scientist, that in Australia, when real men do that demonstration, they don't hold the cannonball to their head, they hold it down there.
Thank you, Richard. Well, okay. Let's thank Professor Richard Dawkins once again. Thank you, Richard. That swinging ball shows that you can't destroy or create energy, but you can convert it from one form to another. So energy comes in lots and lots of different forms. And I didn't want to give you a long, boring list. So instead, I thought we'd do something a bit more fun. And this contraption, right behind me, is called a Rube Goldberg machine. And it's been painstakingly put together by my Royal Institution team over the last month or so. And it's a type of energy cascade and carries on outside this theatre. So I need a volunteer from this side over here. OK, I'll rush over. OK, so would you come over here? So can I take your name first?
Sophie.
Sophie, why don't you come on this side? So let's take a seat there. We'll sit together. So, Sophie, what you're going to do is you're going to help me set off this Rube Goldberg machine by something I prepared earlier, this lovely ball. So if you just hold on to that, and I'd like you to spot how many times energy changes from one form to another. OK? So we need a big countdown for this, OK? Give me a big countdown. 3, 2, 1. It goes. It's going fast. So that is Jacob's ladder with sparks. We've got the fan going off. We've got hopefully a little boat moving. And let's see. Amazing. OK, let's see it's going to go out of the lecture theatre. Here it goes. So look out for those conversions. OK, it knocks out. There's some kinetic energy, elastic energy. Look at that. It's down the corridor down there. It goes. The car. More of a domino effect. This is one of my favourite bits, the wave. Nice wave there. It's a plasma ball. This is a chemical reaction producing a fluorescent material. If you watch, it's going to go down this circular wire. Look at that. And then, so if you see, it's going to turn this bicycle wheel. And then it's going to pass that. That was a magnetic track. Okay, let's see what's going to happen next. So you can watch out for another chemical reaction. It's going to fix that. So this is out the side. It's going to knock over those balls. Hopefully it'll set off. That ball is going to come back, hopefully, very soon, through the corridor, through here. Back into here, watch out for it. Yeah! Yes. So, I gave you a test or exam at the beginning of that, and the number of energy conversions. So does anybody have a guess of how many there were? Anybody shout out a number? 15? 20? So who's going to go for 15? Who's going to go for 20? Who's going to go for a lot more? Well, the actual answer that we worked out is roughly, it's about 111 with different energy conversions. So when we think about energy in our daily lives, we often think about one thing, and that's electricity. But we don't often see electricity in the raw. So I want to make electricity a bit more visible. So could you please welcome Derek Woodruff, electricity experts. Let's go around that side. Nice to see you, Derek. I love your contraptions here. I know they're two separate Tesla coils. They make people here at the Royal Institution a bit nervous. The last time they had a Tesla coil here in this lecture theatre, it fried all the fuses and it turned all the computer text German. But these two Tesla coils are different. They've actually learned to play music, German music. So, Derek, take us away. If you could dim the lights as well. Right, so what you've seen there is basically a flow of electrons. Electrons carry charge. So these Tesla coils build up a huge amount of electrons or negative charge. There's such a big build-up of electrical charge, it's released in a single burst of electricity, or spark. That turns air into a conductor. And where else do we see this? Well, as you can imagine, it's lightning. So during really violent thunderstorms, you get that big build-up of charge. So why are these ones a bit musical? Well, changing the frequency of the sparks, that means that these Tesla coils can play different notes. So I think we want to hear one more. Thank you, Derek. And
pleasure.
Auf Wiedersehen. Okay, so let's get back to electricity. Electrons always take the fastest route to where they want to go. Travelling through the air isn't easy for an electron. In contrast, travelling through metal is a lot easier. So if you create a metal pathway for the electrons, they should always follow it. I wanted to test this out, so I sent Christmas lecturer, Professor Monica Grady, to the biggest Tesla coil we could find. Hello, Monica, over to you.
Hi, Saiful. Hi, everybody. And look what I've got here. It's a Tesla coil, and it's much more powerful than the one you've seen operating already. I am going to get into this Faraday cage here. Now, Faraday cage is named after Michael Faraday of Royal Institution fame. How it works is the current passes across the wires and it doesn't go into the cage. So I will be quite safe sitting in there, but I'm still going to wear my Wellingtons when I get inside, just in case. Right, well, I'm going to be locked in a minute. It does feel a bit bizarre, but what I've got here is I've got a safety pad, and that goes under my foot. And while my foot is on it, the discharge will work. As soon as I take my foot off, everything stops. That's part of the safety apparatus. I've been instructed not to try to put my finger through any of the holes. Definitely not to touch the wire. And just for once in my life, I'm going to be very, very, very obedient. Don't like this. I think it's better if we get it over with soon. So, take it away, Colin. Wow, that was stupendous. It's one of the really bizarrest experiences I've ever had, and just really, really strange. And I never felt a thing.
I have to thank Monica, rather her than me. If you don't know about the science, you might think that this was very dangerous. I can safely predict that you've all been inside a Faraday cage. All the metal cars that you've driven in or been in, they are Faraday cages. That's good to know if you've ever been in thunderstorms. So these Tesla coils have been great, but the electricity they produce is just an uncontrolled burst, an uncontrolled spark. So what we need is a smooth, steady flow of electrons. So we're going to have to find another way to power our theatre. We need an electrical generator. So this brings us back to Michael Faraday, the founder of the Christmas lectures. And actually, he's one of my scientific heroes. He came from very humble beginnings rather than the wealthy elite. But he went on to discover a huge amount about the fundamental nature of electricity. So one of his inventions was this strange contraption coming in here. It may look like a bit like a burnt sausage, but actually, this is one of the treasures of the Royal Institution. And our curator, Charlotte, thank you, Charlotte, for coming in, is going to hold it for me. I'm not allowed to touch it. So believe it or not, this thing here, this tiny machine, totally transformed the way we live. It was the spark that ignited the electric revolution. And it's really the first electrical generator. So how does it work? Well, what it's made up of is it's got this metal magnetic rod, as you can see there, and it's actually covered by these copper wires. And as you move that metal rod in and out through there, that magnetic energy and that movement generates electricity. So it's an energy conversion. So machines based on this simple contraption power the modern world. So thank you, Charlotte. So how does a modern electrical generator work? So let me show you through this contraption here. So before that, the one that Charlotte brought in was a static ring where the metal rod went in and out. Here, and if the cameras can get close, you can see now we've got these copper wires again, but this time the magnet is rotating. I'll show it slowly first. You can see the red and the greys. So let's rotate. But if you spin it fast, you can actually begin to generate electricity by that magnetic energy and that movement. And since it's moving continuously, much faster, it's much more powerful. So this is the basis of almost all modern electricity generation. But I'm not muscular enough to actually turn this, so I need somebody a bit more muscular. I need a volunteer. So one in green, yes. Come on down. Hello there. So can I take your name first?
Daniel.
Daniel, well, thanks for coming down. What I'm going to try and get you to do is that we've got some lights here, so don't start yet. So you've got some lights here, and by turning on each one, it kind of increases what is called the load, kind of gets more difficult. So if you turn it now, you'll find it's quite easy, isn't it? It's not too bad. So let's see if you can do the bottom one. Let's do that one, and then the other ones. You got that one? It's got just a bit faster. I think you can do it. That's it. You got them right. Right, great. Well done. Thank you, Daniel. Thank you. Got back up there. Thank you. So Daniel there converted his muscular energy into kinetic energy and into electrical energy. So let's go to this energy meter again, the kind of scores on the doors. So this is our target. How much does that hand crank generator give us? unfortunately, a measly 12 AA batteries. Okay? So even if Daniel was at that for a long, long time, he wouldn't really generate enough to power this lecture theatre. But can we use this principle to get us closer to our target? And here, I need 2 more volunteers. Okay, the one at the end there, and if you want to come down. Okay, if you want to come down, on the inside. Can I take your name?
I'm Dan.
Dan?
Alex.
Alex. Okay, so we're going to send you on a bit of a journey. Not too far, it's just a journey within the Royal Institution. So if we could have a couple of our production team to take you away. Okay, Dan and Alex, thank you. So over the past few weeks, my team here has rigged the Royal Institution with lots of different types of energy generators and thrown in some newer technologies as well. So as you came into the building, I don't know if you've noticed, you walked over a very special floor. It generates electricity out of your footsteps. And it works a lot like a Faraday's generator. So I think we've got some footage. So there, that's the one. Basically, those steps were pushing magnets into copper coils. So it's a bit like the electrical generators I showed you as a display and that rod. And it generates a small electric current. So how much energy or electricity did it generate? So let's go back to our energy meter. So it was just for over a week. And if you see, if it comes down, yes, just 1 AA battery. We didn't cover a large area. Obviously, a large area would have done a lot better. So up on the roof, you may not believe it, but we actually got a fully functional wind machine and wind turbine attached. And that is a live shot right now. And you can see it's been raining. I know some of you noticed. So that is a live shot of the wind turbine. So is it Alex or Dan up there? All right, great. We can see Alex coming. OK, she's coming up the ladder. And Alex, can you hear me?
Yeah.
Oh, great. So we've got the wind turbine up there. Can you go see if you can find out what the reading is from the wind turbine? OK?
4 kilowatt hours.
4 kilowatt hours. OK, well, thank you. Alex, if you want to make your way down. OK, thank you. OK, she said 4 kilowatt hours. We're going to actually try and convert that into our energy meter, which we want to do in AA batteries. OK, so let's see what that value is. So this is our target. It's coming down. This is our wind turbine. And 1,569 AA batteries. So not too bad, and it wasn't up there for too long. We've finally sent Dan to the men's toilet. Because last week we installed a special cell that converts we into electricity. So it's we power. So, okay, so you can see time lapse. You can see it being installed in one of the toilets upstairs here at the Royal Institution. So we've got Dan here. So Dan, again we've got a reading from how much energy that produced from that microbial fuel cell. So tell us.
So we've got 3.78 at the moment.
3.78. OK, thank you. Why don't you make your way back here? OK, thank you, Dan. So I want to say a bit more about that fuel cell. It's called a microbial fuel cell. What it does is it uses bacteria to convert we into electricity. So all the guys at the Royal Institution have been told to use that urinal. So how much energy have we generated from using P power? So let's go back to the meter. As usual, the target, and it goes down to 2. A wee amount, yes. So that's just 2 AA batteries. So many of these methods of generating electricity, particularly things like wind power, are what we call renewable. And that means that the energy is supplied from sources that are naturally replenished. At the moment, they just aren't giving us enough energy by themselves. That's true for the lecture theatre, And it's true for the whole of the UK. So that means we still get about 50% of our energy or electricity from fossil fuels. So these are fossil fuels such as coal and oil. This is a bit of a dodgy oil. It tells pretty rude jokes. It's called crude oil. But also another fossil fuel is methane. So why do we use fossil fuels? Well, two main reasons. First, they contain a lot of energy. Oh, that was great. So let's see that in slow motion. So you can see there's the balloon, there's the flame. And what's interesting is you see the plastic balloon going off first before you see any ignition of the methane. But it'll happen in a minute. There it goes. There it goes. So that's what I call a real flame. There's another reason behind why we use fossil fuel, is that it's buried under our feet, so we can actually get to it. But how do we turn that fossil fuel into electricity? Well, there's something I've prepared earlier to help me explain. It might not look like it, but this is a fossil-fueled power station. Okay, well, what we've got here is we've got water in this pan, and underneath we've got the burning fossil fuel, in this case natural gas. And what it's going to do is that steam from the water is going to turn this fan here. And that fan is very close to an electrical generator. So you can see the coils here. It's a bit like the generator we saw earlier. And hopefully it will, just by steam, it will light up these lights here. Yes, so you can see it there, the lights going on. And that's just from steam. So in a sense, all power stations can be viewed as giant kettles. The only difference is how we boil the water, either coal or gas. And in nuclear power stations, the heat is from splitting apart atoms, usually uranium. So massive power stations like these generate electricity for the majority of the world's population. I would call them masterpieces of engineering, but we rarely see inside them. In a way, we take them for granted because they generate our electricity. So I asked another Christmas lecturer, Professor Tony Ryan, to go behind the scenes at Britain's biggest power station.
Hello Saiful, hello kids in the audience. I'm here at Britain's biggest power station. It's called Drax and it's enormous. I want to show you how it works and how it scales up from the model you have in front of you in the theatre. The noise in here is incredible. There are 6 generators, each with 5 turbines. They generate enough power for 1 million households. That's the most energy generated anywhere in the UK. And the turbines work just like you've seen in a lecture theatre. Energy gets converted into heat, heat into motion, motion into electricity. You can't see the turbines themselves because they have to keep running, so the lights stay on. But we will go look in one that's been taken apart. Wow, this is enormous. So this is Steve Austin, the Chief Turbine Engineer. So Steve, how fast does this go around?
This will spin at 3,000 RPM, or 50 times a second. The blade tips, they will spin at 1,250 miles per hour, which is 1.6 times the speed of sound.
And how often do you have to look inside them to make sure everything's okay?
Well, we run for 8 years in between inspections. But this turbine in particular had run for 34 years, which is about 270,000 hours in service.
For most of its life, Drax burned coal. But we're going to stop using coal for power in the UK over the next 10 years. So Drax has switched to using these, compressed biomass pellets, and they're stored in these massive domes that are bigger than the Albert Hall. Up and down the country, huge power stations like this are keeping the lights on, the ovens cooking, the homes heated, all operating on the same principles identified by Michael Faraday over 200 years ago.
Okay, thank you, Tony, for that. As we know, burning fossil fuels is a major problem in terms of releasing carbon dioxide, which contributes to global warming. But right now, fossil fuels are still a very useful source of energy. So where do fossil fuels get their energy from? Millions of years ago, coal, oil, and gas used to be living things, plants and animals. And these plants and animals got their energy from the sun. So in the very long term, fossil fuels are essentially solar powered. And this begs the question, where does the sun get its energy from? Right at the start of the lecture, we defined energy as the ability to do work. But there's another way to define energy, through the most famous equation of all time. Anyone know what that equation is? E equals mc squared. There we have it there. E is for energy, m is for mass, and c is a huge number, the speed of light. This was formulated over a century ago by one of the most famous scientists of all time, Albert Einstein. This famous equation tells us a very important fact. Mass, the stuff that makes up the whole world, makes us up, is equivalent to energy. They are interchangeable, just different forms. This tells us a tiny amount of mass contains a colossal amount of energy. So I was racking my brain trying to find a good way of visualizing this. And we've done some very complicated calculations. We've come up with the most sophisticated example. My pants. You'd be amazed at how much energy there is in these pants. According to that famous equation we just said, E equals mc squared, they contain enough energy to power the city of Birmingham. Lucky Birmingham. So let's put it there. So let's put it to the test. We're going to burn those pants. And there is a scientific term for it. It's called burn pants burn. And let's see. Okay, right. In this, just to speed up the reaction, we're going to use some liquid oxygen. And just to see the effects, so let me get this going. Yeah, I've never liked those pants, actually. So is that enough energy, do you think, to power Birmingham? I don't think so. So in scientific terms, we call that liar, liar, pants on fire. And that's because the energy in those pants is hard to get at. My pants are hard to get at as well. Simply setting them on fire only releases the energy of the bonds holding the atoms together. So if you really want to power Birmingham, the atoms need to undergo a series of nuclear reactions, either to split them or fuse them together. And it's only then that the mass releases that vast amount of energy we saw from that equation, E equals mc squared. So this helps us understand why the sun is so powerful. It's converting an enormous amount of mass all the time, mostly hydrogen, into vast amounts of raw energy in the form of heat and light. It's actually the biggest energy converter in the whole solar system. So can we do the same thing here on Earth? And the simple answer is yes, we can. What we're seeing here works on the same principle. It's basically converting the mass of hydrogen directly into energy. It's a hydrogen bomb, the most destructive weapon in the world. But there is hope that we can carry out a more controlled version of this reaction we've just seen, and it's called nuclear fusion. So what is nuclear fusion? So to help me answer that question, I'd like you to welcome from the UK Atomic Energy Authority, Professor Ian Chapman. Hi, Ian. Hi. Thank you for joining us, Ian. This is a very interesting contraption. I know it's related to nuclear fusion. Tell us a bit more.
So to get nuclear fusion to happen here on Earth, we have to get the fuel incredibly hot, sort of 10 times hotter than the centre of the sun hot. So this, obviously, we're not doing that here, but this is a demonstration of what happens when we do that. So when we put the fuel under these incredibly intense temperatures, you make the fuel very energetic. And when you do that, the ions and the electrons, which are inside the gas, separate. So you separate those charged particles, and that gives you a plasma, and that's what you can see inside this cage in here. So this sort of beautiful cloud, this ball of light is a plasma.
Okay, you mentioned the word plasma. So what is plasma?
So plasma is the fourth state of matter. So you have a solid, then a liquid, then a gas, and then a plasma. And a plasma is essentially a very energetic gas, where you've heated up the gas to extreme energies, and the ions and the electrons have separated. So you have a charged ball of ionized gas.
You've brought us another interesting contraption here. So I understand that plasma isn't easy to control. So how do you control plasma?
That's exactly the difficulty with having fusion reactors, is controlling the plasma. So again, we're going to spark a current through this tube. And once again, we have this plasma. But because the plasma is charged, so you have ions and electrons here, it will feel a magnetic field. So I have a simple magnet. If I put the magnet near it, you can see how the plasma is reacting to the magnet, and it moves because the magnetic field is near it.
So let me have a go at that. It looks really good. So basically, just using the fact that it's charged, you can control it with this kind of magnetic field or a strong magnet.
Exactly, and that's how you would go about building a fusion reactor. Because as I said, you have a fuel which is incredibly hot, so you need to keep it away from the wall of the reactor, and we do that by creating a sort of magnetic cage, a magnetic bottle to hold the fuel in.
Okay. Well, will we see a nuclear fusion reactor very soon?
That's what we're hoping for. So we're building a machine in the south of France right now. That will be a proof of principle. It will get 10 times the amount of energy out that we put in to get the reaction going in the first place on a sort of 500 megawatt scale. And soon thereafter, we hope to be building reactors.
Oh, great. Well, thank you, Ian Chapman.
Thank you.
So fusion works on a large scale. It could mean unlimited quantities of electricity with hardly any carbon emissions. Obviously, this is a scientific challenge, and it will take years to crack. So let me return to that giant nuclear furnace in the sky, the sun, the light that never goes out. So did you know that in just 2 hours, enough energy from the sun hits the Earth to power human activity for a whole year? We can already convert the sun's energy directly into electricity using solar panels. And this is something I'm really excited about. It's one of my research areas. So for this next bit, I need a volunteer and somebody who's not scared of heights. Okay, I should come over to this side. I haven't been over there. So yeah, do you want to come through? Come on. Hello. Hello there. Can I take your name? Natasha. It's Natasha. So Natasha, I asked about scared of heights because you're going on a journey as well. So one of the production team is going to take you off to look at some interesting technology. Okay? So back to our big challenge. Can we power this lecture theatre? I've covered the roof of the Royal Institution with solar panels. So this is actually a live shot. And it is live, you can tell it's raining, covered in water. and they've been plugged into a battery. So there's the battery, and that's a live shot, looking very wet. And that line there has gone down, and it's come into this lecture theatre, and that is the line. So we're going to try and test it out. Let's see if our volunteer, Natasha, has got up to the roof. OK, here comes Natasha. She's on the roof, and we're going to try and get to reading of our battery. Natasha, can you hear me?
Yes, I can.
OK, so can you give us a reading from that battery?
Certainly. The power is 110, and that's 4.7 kilowatt hours.
And do you want to read us the number below it as well?
That's 97%.
OK, well, thank you, Natasha. I think you deserve to come back out of the wind and rain. OK, thank you. Let's give us our reading on our energy meters. We've got a couple of readings. So that was our target. And we're down to 2,314 AA batteries from those solar panels. OK, and by the way, I've used a small bit of that electricity to make a solar-powered snack. So watch this. Very burnt toast. See, but that was directly from the solar panels hooked onto that battery and down here. So those panels up there are made of silicon. But take a look at these. These are next generation solar panels, solar materials. As you can see, much more flexible, a bit lighter as well. And they're made of much more exotic materials. Copper, indium, gallium, and selenium. And we're going to hook them up. I'm just going to put this down here. OK, we're going to hook them up to this electric spark generator. And what the solar panel here will do is try and generate electricity directly. And what we need is some, obviously, light directly onto those panels. And in this case, we've got a couple of lamps there. So we need the lights on, OK? And I'm going to turn this. So we're going to probably dim the lights a bit. Yep. So we've done it. We've got some sparks flying just from this panel here and a couple of lights. And the light's off, it stops. So basically, it wouldn't work without that light energy. So new exotic materials and new generation panels like this are really changing how we can use solar design. So how much of the sun's energy can solar panels harness? To understand that, we need to understand light. Sunlight isn't made up of just one colour. It's made up of lots of different colours all mixed together. To show you this, I've got a very bright light to simulate the sun. It's got a special filter that splits light into its component parts. So each one of these colours carries a certain amount of energy. So this is split up, so you can see this here. That's like a typical rainbow that you see, and we are unweaving the rainbow there. But for this, the data on that computer actually is going to read out the different energy levels. But for that, we do need a volunteer. So can I take your name?
Tess.
Tess. So Tess, when I ask you to, can you shout out the numbers that you see on that computer screen? Is that OK? Great. So what we have here is a solar panel, a bit like the ones on the roof that you saw earlier. And what it does is very clever. It tells us the different energy levels across that spectrum. And what it's trying to show us is that there are different energies within the different colours. So let's see what we get from the readout. OK, I'm going to start at the blue end, since I'm on this side here. So Tess, if you could start telling us some values. So it starts off probably at 0. So what have you got at the moment?
8.
8, OK. So let me move along a bit further.
10, 14.
14. So really, when we're getting towards the kind of greeny colour, we're getting to 14. OK. How about around yellow? What have we got for yellow?
12.
12. OK, we're going towards orange.
10.
10. And now the red end. Right down here.
6.
6. So you can see straight away that all the numbers, in a very general way, are not the same. So solar panels can't capture all wavelengths of light. They stop working at certain regions in the spectrum, depending on the material they're made of. Tackling this issue is one of the big challenges of solar cell design. That's one of my research areas as well. But compared to most other things, solar cells are still very efficient. They can already do some pretty amazing things. I want to show you one of my favorites, a plane powered using nothing but energy from the sun. So we're going to speak to the two pilots of this plane, Bertrand Piccard and André Bouchard, right now on the line from Switzerland.
Yes, hello from Switzerland.
Thank you.
Landing now at BBC.
Thank you for joining us, André. Thank you for joining us, Bertrand.
Great pleasure.
Tell us how far you got with your solar-powered plane.
With Solar Impulse, we went the furthest we could go. That means all around the world.
Tell us a bit about the plane itself.
So you imagine the task for the engineers that were led by André to make a plane that was the size of a jumbo jet, 236 feet wingspan, and the weight of a family car, 2 tons. Really absolutely amazing. Nobody thought we could do it. But if you are a pioneer, an explorer, you don't listen to people who say it's impossible. You use their skepticism as a motivation, as a stimulation to prove that you can do it.
What was the toughest part of the journey?
But of course, for us, the difficulty and the challenge was to fly over the oceans. We flew over land with the first airplane, so I think we knew how to fly such an airplane. But to go over the ocean for many days, many nights, we didn't know if the airplane would be able to make it. We didn't know if we could forecast the weather well enough. And of course, we didn't know if the pilot, in fact, could sustain such a long flight.
Because you have to understand that it's an airplane that can fly forever, at least theoretically. The sun is charging the batteries and running the motors during the day flight in order to fly through the night with the batteries and reach the next sunrise. So my flight from America to Europe across the Atlantic was 3 days and 3 nights. And for all this time, you have to be like in the science fiction film. You look at the sun, you look your electric motors turning, you think, wow, that's the future, that's a fairy tale. No fuel, no pollution, no noise, flying forever. And it's not the future. What is magic with clean technologies is that it is the present. It's what is allowed now by renewable energies.
So we currently see planes carrying 200 to 300 people. Do you ever see a time when solar power planes could do the same?
I would be crazy to answer yes and stupid to answer no. Because today we don't have the technology for that. But Charles Lindbergh neither had the technology to do it when he crossed the Atlantic in 1927. And nevertheless, it happened.
Thank you, André. Thank you, Bertrand. Bye-bye for now.
With pleasure.
Bye-bye.
Bye-bye. Take care.
Bye-bye.
Solar power is unlikely to give us all the energy in the UK because we have a limited land space. And it's a challenge during the winter months, at least here in Northern Europe. But with more research, they will play a bigger role in the future. So finally, let's return to our big question. Can we power the lecture theatre using the mix of energy sources that we've generated here? Okay, so there's only one way to find out, as ever. Let's look at our scores on our energy meter. So let's have a final drum roll, please. Come on, give us a big drum roll. Let's see how far we got. So first, our candles. And it was a little blip about a special floor. Tiny. Our wind turbine, a bit better. Our wee power, yeah, a drip really, isn't it? And lastly, our solar panels, there. And that gives us a total of 3,937 AA batteries. Well, even with all that clever equipment, we've not made it. That's because this lecture theatre and society as a whole is incredibly energy hungry. To reach the target in a week, we'd have to use 9 times as many solar panels or 14 wind turbines on the roof. Unless, of course, we unlocked the energy in these, my pants, through nuclear fusion that will light up the whole of Piccadilly. I'm optimistic. The energy gap will be filled. And as this is our 80th anniversary, I want to celebrate. So please welcome one of the stars of this year's Great British Bake Off, Selassie. Great. Yeah. Great to see you.
Great to see you, buddy.
Welcome, Selassie. Thanks for joining us. You were one of our family favourites. What was it like being on the Great British Bake Off?
It's really fun, so if you ever change your mind about science, you can, you can go and buy. It was really, really fun, very challenging.
So could you begin to ice that last cake there while I explain what we've got here? So these cakes represent the different years and the different amounts or proportions of energy used in the UK to generate our energy. So 80 years ago, it's our 80th anniversary, 1936, and you can see the big, gigantic black slice, indicating that coal dominated 80 years ago. And we've come on a long way. So if you now go to this year, renewables in green, coal in black. For the first time this year, the UK generated more energy from renewables than from coal. So our goal in the future is to double our renewables. So this last cake that Selassie is beautifully iced represents our ambition. So not since Faraday's day has there been a more exciting time to inventing new ways of generating energy. So get thinking. Your ideas make a difference in the future. In the next lecture, we're going to look at how humans and other animals use energy. So join us to find out if we can supercharge the human body. Thank you and good night.